So this video is about scientific notation. So let's first just talk a little bit about scientific notation and what it's for. If we look at what I think we were talking about the radius here, the radius of the observable universe, and since the information I have is actually a little bit dated from I think 2011, I'm sure it's much larger than this, but well, maybe not, because of the magnitude of the number. It's not going to be significantly different from what's there. Of the observable universe, and that would be 100 trillion meters. And how would we write that number? Well, it's 1 and 26 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. That is a pain in the tuchus, and it's cumbersome, and it's rife for, or primed for, error, right? What if I just forgot one of my zeros? That's a significantly different number. It's actually not 10 less, it's 10 times less. So that would be the equivalent of saying, oh, I was 6 feet tall. Well, clearly I'm not 6 feet tall. I'm just picking a round number. I'm 6 feet tall. Oh, actually, it's not clearly to you because you haven't seen me. But anyway, I'm 6 feet tall. No, I'm 60 feet tall. That's a magnitude difference of one magnitude, or 10 times. So 10 times is a large difference. Even though it's not large in the scope of this size of a number, it's still 10 times larger. So we have a system with which we can use to write this more efficiently, and that would be 1 times 10, and then the layperson's method is to count the number of zeros that are there, 26, and that's effective. It's perfectly fine. What we're really doing is we're trying to figure out how many times we can divide this number by 10 to write it this way. Or, even better, if I have 1, how many tens do I have to multiply this by to make it that value? Well, it would be 26, right? 1 times 10 to the 26. Well, and since 10 to the 26 times 1 is the same, so you can also be even more efficient and just write it as 10 to the 26th. So scientific notation has some rules around it. So this number, if we were talking about, let's say we're talking about some other value that was something like this, 3 times 10 to the 13th. This number here, this front value, must be greater than or equal to 1 and less than 10. So this number, which is here, this lead number, must be greater than or equal to 1 or less than 10. For instance, if I had 2 times 10 to the 15th, perfectly fine. 2.714 times 10 to the 12th, perfectly fine. 32 times 10 to the 9th, not so much. This number is greater than 10, so it doesn't work, so I need to write this as 3.2 times 10 to the, and I would have to multiply this number by an additional 10 to make these equivalent, so those two things are equal. Or if I had 0.07 times 10 to the 5th, really I need this decimal place to be here to follow the rules that this lead number has to be between 1 and 10 and can equal 1 but not 10. So I'm going to have to move this back. So what do I have to do? I have to divide this number. So this is going to be, oops, I turned on the eraser. 10 to the negative third. I'm sorry, not 10 to the negative third, 10 to the third. Did I just goof that up? Yeah, no, that's fine. Sorry, I'm doing two things at once, which maybe I shouldn't do. Okay? you're going to be asked to do some things with the metric system, and I suggest that you go find a table of metric system prefixes. They are in your textbook on page, or there's a group of them at the end of chapter 4, but also there's a small table of them on page 214 in section 4.1. It lists pico, nano, micro, milli, centi, kilo, mega, giga, tera. And it shows you the abbreviations for them, like micro is mu. Micro is mu, looks like that. And pico is P. And milli is M, right? Because if I'm writing millimeters, I write this. Centimeters, I write this. This is also the abbreviation for meter. And so you're going to have to be able to navigate the metric system. So let's just give one quick example of the metric system in use. So the easy one, we'll talk about length here. And so if I had something that was 1 meter, and I wanted to represent a value that was, or something that was longer than 1 meter. Let's say that it was 1 kilometer. Okay, well that's the same as saying that it's 1,000 meters. So I'm talking about something greater than, this is 1 meter long, this is 1,000 meters long. A way to equate that to how many meters it is because it's 1,000 meters. 1 kilometer is equal to 1,000 meters. Or you could say that it's equivalent to or equal to 1 times 10 to the third meters, or 10 to the third meters. 1 kilometer is 10 to the third meters. If I want to go smaller or lesser, shorter, I would go in this direction. Let's say we're talking about centimeters. That would be 100 centimeters is in 1 meter. And so it's 0.01 of a meter, because these are smaller. So this many are in there, and this many of these is in here, right? So this is 100 centimeters. Let's correct that. 100 centimeters is equal to 1 meter. Over here we're saying that 1,000 meters is equal to 1 kilometer. So how would we write this in scientific notation? The centimeter action, it would be, move that decimal place 2 places, so it would be 1 times 10 to the negative 2, or 10 to the negative 2, which is equivalent. And that's scientific notation. That's the metric system work. There's probably some other things that might be helpful when we're talking about tens and we're talking about exponents. We might want to review this sort of thing. So 10 squared is the equivalent of 10 times 10. So remember, this thing is actually called a power. The big thing, all of it together, is called a power. And I know as mathematicians we always say a whole bunch of things wrong. I'll give you an example. Y equals mx plus b. This is the slope, that's my y variable, that's my x variable. Technically, a bunch of us, including myself at times, will call this the intercept. But b is not the intercept. B is not the intercept. An intercept is a point. Okay? So that means if the intercept is a point, it's the point where the line or a curve or any kind of other graph crosses the, what did I say, y-intercept? Yeah, y-intercept. It crosses the y-axis. So if this is the y-intercept and it crosses the y-axis, it's a point on the y-axis. Well, what's the x value for any point on the y-axis? 0. So the point that we're talking about, which is actually the y-intercept, is 0, comma b, whatever that b value is. So technically, this is the y value of our y-intercept. It's not the intercept itself. But of course, as mathematicians, we shortcut and we kind of mix things up, if you ask me. So this thing is called a power. The 10 is called the base, and 2 is the exponent. And that's just factually correct. So when I say, oh, it's raised to the power of 2, technically that's not correct language. It is 10 with an exponent of 2, or 10 raised to the exponent of 2, not to the power. The whole thing is called the power. Okay? And later on in the semester we will talk about power functions that look like this, or if you prefer f of x notation, that's a power function. So these mean the way this works, this is just review, right, is that I have some base and I have some exponent. Together they construct a power, and this 2 tells me to multiply this base in this manner. Now, I don't know how to say the language any better because I'm really only doing multiplication once here. So I'm taking the 3 and multiplying it twice. That's really not true. You're only multiplying 3 by 3 one time. But I know that's how we say it. It's how everybody says it. It just always bothers me, and I don't have a better way to say it. So I'm saying that 3 squared means 3 multiplied, 2 3's multiplied. If I said 10 squared, as I had written above, that's 2 10's multiplied. If I have 10 to the 15th, that's 15 10's being multiplied. So that would result in, of course, this number with 15 zeros behind it, right? However many they're going to be. If, for instance, if I had 10 cubed and I want to divide it by 10, hopefully all of you go, yeah, well, that's 10 squared. But if you're getting jammed up, or you're kind of not understanding, or maybe you're doing 16 things at once, like I sort of am doing right now, you could easily just write, well, this means 10 times 10 times 10, and I'm dividing it by another 10, but oh, wait a second. These 2 10's right here, I know you prefer the word cancel. I do not. You can use whatever your word, I don't care. Whatever word you want. I'm just going to not use that word when I'm doing my video, so understand that's where I'm coming from. This 10 divided by that 10 is 1. That leaves me with just those 2 10's being multiplied, which is 10 squared. And of course that's the same as that. If the process didn't work, then math doesn't work. But it does. So 10 squared is equal to 10 squared. So irrespective of how you think about it, how you go about it, you should get the same value. If I had something like, let's say, 4 squared, and I wanted to divide that by 2, well, it's not going to work out so well. I might need to expand this numerator, and let's say 4 squared means this, of course, and then maybe I can divide this and get 2 times 4, which is 8. Or if you prefer, since most of you probably go, well, 4 squared is 16, and then I can just get 8. Perfectly fine. All right? We can also do the following. Let's go back to 10 squared over 10. Of course, I'm sorry, that was 10 cubed over 10 is 10. I'm sorry, 10 squared. And if then I take 10 squared and divide it by 10 again, what am I going to get? I'm going to get 10, right? Because remember, that equals 10. And if I take 10, let's make sure I'm explicit with what I'm doing here. I'm taking this previous number and placing it there and dividing it by 10 again. I'm going to take this number and place it here, and then I'm going to divide it by 10 again. And 10 divided by 10 is 1, right? What if I take that number and put it over here, but again, once again, divide it by 10 one more time? Well, what's that going to be? So let's look at the exponents as we go along here. I had 10 cubed, and when I divided by 10, it became 10 squared. When I took 10 squared and divided by 10, I got 10 to the first, right? And then if I take 10 to the first and divide it by 10 again, I'm going to get 10 to the 0, which, by the way, 10 to the 0 is 1. Anything to the 0 is 1. Anything raised to the 0 is equal to 1. So this exponent, notice how it's going from 2 to 1 to 0. So this, if I follow the pattern, is really 10 to the negative 1. And if I take 10 to the negative 1 and divide it by 10 again, I'm going to get 10 to the negative 2, and so on. So that's a little quick review for us. And I think that's mostly it for this section. Yeah, that's going to be it for this section. If you need more review, you can Google, or you can ask me, or you can email me about scientific notation. But this first section, 10.1, is about scientific notation and and the conversion between different metric prefixes. All right.